Once, Mars wasn't dead the way it is today. It had rivers, it had lakes, and in some ways it looked eerily similar to Earth. So why is it now so dry and defenseless? The answer isn't on the surface, it's inside the planet. Mars's engine aged too early. And the truly frightening question is this: could the same thing happen to Earth one day? A planet's interior can be hot, but here's the bad news: that heat doesn't like staying inside. Heat wants to escape. And where is the exit? The surface. So the planet's cooling lid is essentially its surface. Even with no wind, even with no oceans, the energy inside will eventually reach the surface and leak into space. A planet is basically paying a slow, constant heat bill. Now, to understand Mars, we need to put size, mass, volume on the table first. Mars is about half Earth's diameter, roughly 53%. But when it comes to mass, the contrast is harsher. Mars has only about 10% of Earth's mass, so it's roughly 9 to 10 times lighter. And in terms of volume, the story matches. You could fit about 6 to 7 Marses inside Earth. So Mars isn't just a bit smaller. In terms of its internal heat reservoir, it is genuinely smaller. Here's the critical distinction. Volume stores heat, because the mass that carries heat is inside it. But surface area is what lets heat escape. So think of it like this: surface area to the radiator that leaks heat, volume to the furnace/tank that stores heat. And now comes the ruthless physics: the surface to volume ratio. On small planets, surface area is disproportionately large compared to volume, meaning small tank, big lid. The clearest analogy: a big pot of soup cools slowly. Spread the same soup thin on a wide plate, and it cools instantly, because on the plate, the space-facing surface is much larger. And you can think of the steam as the atmosphere. The larger the surface, the more chances things have to escape. We can even tell the math like a story. Surface area grows with the square of diameter. Volume grows with the cube. So the smaller a planet gets, the more surface you have per unit of volume, and the faster it loses heat. So why is that cooling such a big deal? Because as heat drops, the planet's interior becomes calmer. And it's not just lava that calms down. Mantle convection weakens, internal dynamic energy decreases, and most importantly, the mechanism that generates a global magnetic field struggles. Here's the key message: a planet's magnetic shield isn't just rock and dirt. That shield is the product of a spinning engine inside. And when we get to Mars, the story turns dramatic. Because Mars is smaller than Earth, it lost its internal heat faster. Over time, internal flows slowed down. The magnetic dynamo couldn't be sustained. Mars lost its global shield. Mars's tragedy is simple. Its engine ran out of fuel too early. Earth is still like an engine that's running. Mars is like turning the key and getting nothing. But scientifically, we should be careful. Is it only size? No. Size isn't the only factor. Even two planets of similar size could end up with different fates. Because a planet's heat budget also depends on things like its initial internal energy, the amount of radioactive elements, water/volatiles in the mantle, which affect convection. Crust and tectonic style lock that section with one sentence: size sets the direction, but it doesn't write destiny by itself. And the final line, tied back to Mars. That's why Mars paid the price of being a small planet. It lost heat faster, its inner engine weakened, its shield went dark, and once the shield was gone, the atmosphere was no longer locked in. Space began to slowly erode everything away. On Earth, the outer part of the core is made of liquid iron. Fueled by heat, that iron moves in flowing currents, swirling, rolling, convecting like a giant planetary mixer. And that motion works like a generator, producing a global magnetic field, the planet's invisible shield. But as a planet cools, that internal motion weakens. The liquid iron slows down, convection fades toward a standstill, the dynamo loses power. The result? The magnetic field dims, and the planet's greatest invisible defense starts to fail. And this is where you might ask, what does heat inside the planet have to do with the atmosphere? The connection runs through the shield. Because if the magnetic field is weak, the stream of charged particles from the sun, the solar wind, can begin eroding the upper atmosphere over long timescales. The atmosphere doesn't vanish overnight, but without protection, it can be steadily thinned and worn down for years, centuries, and beyond. Picture it like this. It's pouring rain outside, and instead of a real umbrella, you're holding a tiny cocktail umbrella. Technically, it's an umbrella, but the rain still hits you. That's Mars. Once the shield weakens, the solar wind starts battering the atmosphere, not drop by drop, but atom by atom. That's why Mars's atmosphere didn't disappear in a single night. The solar wind isn't a vacuum cleaner that whoosh sucks everything away. It's sneakier. It behaves like sandpaper. Day after day, month after month, year after year, it slowly scrapes at the upper atmosphere. And sometimes major solar storms arrive and accelerate the process, like the wind suddenly getting stronger. If the magnetic shield is weak, the atmosphere has no umbrella to hold on to. Mars's thin, almost there, almost not atmosphere is the fingerprint of that long erosion. So where did the water go? Not the way most people imagine. It evaporated and instantly escaped. Water was lost in a more cunning way. Water vapor rises into the upper atmosphere, and there UV light from the sun splits it apart. H2O yields H plus O. Hydrogen is incredibly light, like a balloon. Once it's free, escaping into space becomes easy. The leftover oxygen doesn't always behave the same way. Some can escape too, and some can be trapped, binding to the surface, getting locked into rocks. And this doesn't happen over days. It repeats over thousands and millions of years. Mars didn't lose its water all at once. It lost it drop by drop, atom by atom. And that's why today we're looking at a Mars that is steadily drier and steadily more defenseless. Would Earth ever die the way Mars did? Yes, but not today, and definitely not tomorrow. Earth's inner engine is still running. Heat and flow inside the core continue to feed the magnetic shield. Some rough scientific estimates suggest that the core fully solidifying is a process on the scale of tens of billions of years, and some popular summaries even throw around a huge number like approximately 91 billion years. And in practice, what's likely to challenge us first won't be Earth's core cooling down, but the Sun's long-term evolution over billions of years. So don't worry, Earth's core cooling and the magnetic shield fading isn't a disaster on our calendar. It's an unimaginably slow cosmic story. Our real threats are far more near-term. A planet-killer asteroid on the wrong trajectory, a large-scale nuclear war, a runaway AI crisis, or, if our luck is truly terrible, an alien invasion scenario. Mars teaches this. Planets die slowly, but civilizations can disappear very fast because of bad decisions. If you enjoyed this video, don't forget to subscribe to our channel and hit that like button and share it with the people you care about, so the light of science can reach everyone.